Welcome everybody to our joint webinar today together with Infineon. Before we start, I saw that there was a question already regarding the audio function. So all participants in this webinar are muted. I will give you some more details on how we handle the Q&A during the presentation in a few seconds. My name is Florian Süßmeier. I'm responsible for product marketing at Tasking, and I will be the moderator of today's webinar. During the next 60 minutes, our senior field application engineer, Roger Smith, together with Neil Manson from Infineon, an Aurix product application engineer from Infineon, actually will guide you through the specific performance boosting features of the Aurix microcontroller and the main tools and features of the Tasking VX toolset for Tricore Aurix. And they will provide a set of guidelines for designing a high-performance state-of-the-art Aurix-based solution using the Tasking embedded software development tools. Here we see on this slide the Tasking vision. We are actually active partners with leading OEMs and tier ones, and our focus is safety critical software development on multi-core architectures. Tasking provides a complete development environment that allows software engineers to develop reliable, safe, and high performance applications. Let's have a quick look on our portfolio, on our product overview. We are active in regards to the software development V-cycle and provide tools that can be used in different stages. For software development, for example, we are offering the Tasking VX toolset consisting of a compiler, linker, locator, and simulation debugger developed according to ASPICE Level 2 and TÜV certified according to ISO 26262 up to ASIL D. In addition, with the latest qualification kit, Tasking is now also supporting IEC 61508 up to SIL 3 for industrial applications. Supplementary, Tasking is offering LAPAC performance libraries and qualified C libraries as per ISO 26262. The Tasking embedded profiler and the Multicore performance tool support part of the integration testing. In addition, we offer a static analysis tool, the so-called Tasking safety checker, to ensure freedom from interference. And just released last month, the automated detectors in the Tasking inspector tool optimize your errata management, removing the need to perform manual code verification by hand and to stay in complete compliance with industry standard safety regulations for the life of your project. And for hardware configuration, the Tasking pin mapper completes the portfolio. This webinar will be recorded and will be available on demand after the webinar is finished. You can see here the link to our website. So if you are not, if you do not agree that this webinar is recorded, then you have the chance to leave this webinar now. In regards to questions and answers, you can see here in the Zoom function, the Q&A button on the bottom on the right side. You can enter your webinar questions here, and your questions will be then answered at the completion of the webinar at the end during the Q&A session. So now let me introduce our speaker. One of them, Roger Smith. He's an electrical engineer with over 25 years of industry experience, designing, implementing, and debugging automotive electronics. The last 12 years he spent as an application engineer supporting braking, EPS, passive safety, and ADAS applications for a global leader in automotive semiconductors. And currently, Roger is a senior field application engineer for Tasking, supporting a wide range of multi-core embedded software development tools for the North American region. So I will hand over to Roger, and
thank you, Florian,
Sorry.
for the kind introduction. Tasking would like to extend a special welcome to our distinguished guest from Infineon Technologies, Neil Manson. Neil is a lead principal product application engineer at Infineon, specializing in support for Aurix microcontrollers and functional safety. Neil has 15 years of Tier 1 and OEM experience and has been with Infineon since 2013. Without further ado, I turn the presentation over to my friend, ex-colleague, and more importantly, Aurix expert, Neil Manson.
Well, thank you, Roger. Thanks everyone for joining us today. So we want to talk about the multi-core aspects of the Aurix today. So on our latest designs, the TC3X family, we have up to 6 cores on the TC39. So we've got more performance than ever before. But the question then, of course, is how do you split your application into multiple cores? And how do you best fit your application into the Aurix architecture to get the best performance? So what kind of tricks can we do in hardware and software to help you get the best performance in your application? So to start with, we've got specialized multi-core architecture in the TC3X family. So we are a very hard real-time capable system. We have symmetric and asymmetric processing. We've got the HSM core, the Cortex M3 running at 100 megahertz in addition to our tri-cores running at 300 megahertz. We have hardware and software support for virtualization, especially the upcoming TC4X family will have a lot of features for hypervisors at the hardware level, and you can run virtual versions of the Aurix on the PC using tools like Synopsys. So very easy to simulate a system before you begin with the actual hardware. And of course, we're ISO 26262 ASIL D compliant. So we were the first microcontroller on the market to adhere to the new 2018 version of the standard with the TC3X family. We've been doing multi-core since 2012 when the first Aurix was in production. So we have a lot of experience with safety applications with multi-core architectures and very strong partnerships with our hardware and software partners to make compilers, debuggers, and so on. And we've got the best support at every development stage of your project. So we have support through our tool partners like Tasking on software development and tools. We've got dedicated training and documentation available through Infineon and through our partners, lots of application notes and videos out there you can see, and a lot of focus on multi-core tools with our partners to get the best performance out of the Aurix. So a very quick overview of the architecture of the Aurix. Again, we're a safety and hard real-time performance is our specialty here. So we have our CPUs connected together. Each one has its own local CPU memory, and then we have shared memories like the LMU, the local memory unit. And this is all in a very predictable architecture. So we don't have automatic cache coherency at the hardware level, but that lets us have very deterministic real-time performance. These CPUs are all connected together with a system resource interconnect that's a full crossbar bus. So we can do many operations in parallel, like CPU 0, for example, could read CPU 1's memory at the same time that CPU 2 is accessing something from P-Flash. So those can happen in the same cycle to improve performance. Then down at the lowest level, we've got the system peripheral bus. That's a little more limited. It's a 32-bit bus width and 100 megahertz speed. And that's where all of the peripherals like CAN and SPI are connected to that bus. We have dedicated scalable instructions for multi-core synchronization for things like grabbing semaphores with a read, modify, write instruction. And we have extensive safety mechanisms. You can see this SMU box, our safety management unit. We have hundreds of safety mechanisms like ECC protection on all of our RAMs and the flash memory, voltage monitoring and more flows into that safety management unit. The idea here is that we can take a very fast path to asserting some safe state on a special output to get the system into a known safe state where whatever that soft error was can't affect the operation of the system. So the first workflow to write a multi-core application is to learn about the Aurix, of course. We analyze the use case. So we look thinking about the application. How can we split it up? What are our real-time constraints? And to help with that, we've got documentation on multi-core programming. We've got the 10,000 pages of Aurix documentation itself, the user manual, the data sheets, application notes. We have training partners like MicroConsult that you can lean on. We have the next step is to look at the multi-core software design. So how do we want to map objects in RAM to get the best performance? How do we develop the multi-core software? So that's looking at, especially looking at the performance with debug tools to see how it's working out. And then we can go back if there's a problem and iteratively improve the performance. So we've got all these different software tools. Some of these are debugger partners. Some of these are tools like Selexica and Mtrix that help you parallelize your algorithms. So to look at the first step of how do we acquire multi-core knowledge, well, we've got training partners like MicroConsult. We do hold occasional workshops to help with things like using the GTM or with multi-core performance. These have largely been put on hold due to COVID, but I hope to get back to these in the near future. To analyze the use case, we need to think about things like what tasks are going to run on what cores, how do I map memory into different spaces using the linker, what kind of operating system do I choose on, and that really helps define how you can move things around in your system. So just a quick example in iSystem, you can see at the bottom here, CPU 0, CPU 1, CPU 2, we can measure the overall performance, the overall load on each CPU core and try and shift things around. So we have three basic mapping problems when we talk about multi-core software. We have the functionality, and that's sometimes constrained by what different performance can we get on the different cores. On the TC2X, we had the efficiency core and the performance core with different pipeline, different performance levels. In the TC3X, it's all performance cores, so not quite as important. But we do have to decide whether we need that lockstep or not. So some cores in the TC3X have a lockstep and some don't, depending on what variant you've got. So obviously safety critical code should run on a lockstep processor. We have to think about where we map the code and the data. We want the data always to be close to the core that needs it for the best performance to try and avoid conflicts over that SRI bus that can slow down the system. And then we need to talk about how to map shared data, and that's really complex with the Aurix because we don't have that automatic cache coherency, and where we put that data can really impact performance. So choosing the operating system and what tools you can use ahead of time to analyze performance is really important. When we develop the software, we can do things like put all event-driven tasks on one core, maybe time-driven tasks on another. We can think about how to split tasks across cores to balance performance. And sometimes you might even have one core strictly servicing interrupts. Maybe it doesn't have an interrupt at all, or maybe it has some very fixed algorithm that doesn't require an operating system. And then sometimes we split tasks up by ASIL levels so that we have something like CAN diagnostics, for example, running on a non-lockstep core. And then sometimes you may have an OEM giving you black box code to run with the Aurix architecture. That can be a big benefit to have a CPU core that's available for nothing but that task. You can have that task run on its own core. You can use the safety features in the Aurix to wall that core off so that it can't have any freedom from interference problem with the other algorithms. as a quick example, here's a system that has one core devoted to AUTOSAR functions in CPU 0. The second core might be doing a non-AUTOSAR task. So maybe it's doing something like DC to DC, very fast interrupt switching, where it doesn't have that operating system overhead. And you might have the hardware security module, that ARM core, doing CAN authentication. So in the background, it's doing CAN encryption and decryption of messages. And here we've got one MCU covering the whole application. We've got easy software development because we've got a very AUTOSAR domain on CPU 0, very non-AUTOSAR on CPU 2. We've got simpler safety concept because those things are split apart.
So a fun fact that most people don't know is that tasking does more than just compilers. So within the tasking product portfolio, one of the performance tools available is the embedded profiler. The embedded profiler locates performance hotspots and identifies the lines of code consuming maximum CPU clock cycles or stalling of the CPU. So we trace instructions, performance events. You can see here in this little snippet here that we've been able to actually go down to the line of assembler code and highlight the number of stalls that have occurred due to memory access delays or branch prediction misses. We're capable of detecting cross-core and concurrent memory accesses. And a new useful feature is that we can identify application bottlenecks by tracing, analyzing, and profiling the DMA performance. And a key embedded profiler feature is that it can identify unfavorably aligned jump labels within frequently called functions. So for example, if you shift the address of these functions to a half-word, word, or double-word aligned address, you can increase the application's performance.
All right, thanks, Roger. So another way to look at the performance is with debuggers, and different debuggers have different features here, but this is an example of iSystem looking at the AUTOSAR level of code. So you can definitely look down at a lower level with iSystem at the assembly level, but they have nice options to display at the AUTOSAR level what the overall task utilization, what the overall task state is here. So you can see this core 0 task write code, how it's bouncing between suspended and ready and running. So very nice display options there from partners like iSystem. We can also view instead of viewing at the time domain like this with a oscilloscope kind of view, we can look at the overall statistics. So we can see over time what percentage of the CPU is going for each task. And in this case, we've got these runnables instead of functions because we're looking at the operating system level. And to get more information about iSystem, you can click on this link at the bottom here. So when we talk about optimizing the distribution of the software, we can shift tasks around to get the best performance. There are tools that let you do this in a virtual domain, like Synopsys, so you don't have to run on the actual Aurix target. You can simulate that on the PC. And Synopsys includes not just the tri-core CPUs, but all of our peripherals on the Aurix as well. So that's something that the OEMs are really looking at lately to try and reduce the overall time it takes to integrate all these ECUs together. They're actually running multiple ECUs in this virtual domain. But in the real world, what actually happens is instead of following this nice workflow, we see customers just write their application without worrying about it too much. And it turns out that it's too slow. So what do? They call Infineon or tasking to work some last minute miracles. So let's see what those last minute miracles generally consist of. We have an application note 32350 that is a good multi-core software development for Aurix. It's got some little cookbook tips in it, and the most common things to improve performance are try and keep code as much as possible in the local program scratchpad RAM of each CPU. That's 0 wait state, very limited RAM, but it's there to really improve performance and keep data in the local GSPR as much as possible. Try and enable program cache or data cache so that you get the benefit of having constant data. Remember that flows in our Harvard architecture, we have separate flows for program, for instructions and data. So having data cache enabled even for constants in pflash still makes a big performance difference. Try not to have globally used variables in the data cache. You can either use direct addressing in the local memory unit or manage the cache yourself. But again, cache coherency in the Aurix is not automatic. And we try to avoid potential memory access conflicts that reduce performance. So if we have a lot of global data stored in CPU 0's RAM, for example, and the other CPUs 1 through 5, let's say, are hitting that RAM nonstop, that can actually reduce the performance of CPU 0. And finally, use test, and set spin locks. So that means instead of just doing a read, modify, write instruction to try and grab a semaphore, for example, you can read it first to see if it's clear and then do the atomic instruction to try and grab it. And that can really improve performance.
All right, thanks, Neil.
Yep.
So at this point in the discussion, let's transition to a short demonstration highlighting the performance aspects of the Aurix when combined with the tasking Tricore VX toolset. So in this particular portion or this benchmark, we'll be utilizing the Infineon TC39X evaluation board here primarily. When we look at the software that we'll be running, we'll be using a tasking modified mbench open source piece of code, which I'll talk about a little bit more in the next slide. And then we'll be using the tasking Tricore version 6.3 R1 Premium Edition for Windows. And just to highlight again, the performance, or the purpose is that we want to evaluate performance aspects of the Aurix architecture, and we want to demonstrate how the tasking software development portfolio can increase the performance of your Aurix safety application. So if we look at mbench, what is mbench? So mbench is a free and open source benchmark suite. The benchmarks are designed to test the performance of deeply embedded systems. And these benchmarks are largely derived from the Bristol and NBCosm benchmark suite, which is available at the, more details are available here at the URL. So the benchmarks can be used to yield basically a single consistent score for the performance of a platform and its compiler tool chain. And you can see here I've expanded the project here inside of the tasking workspace, and you can see the 19 different sub functions that make up the mbench open suite software. And so tasking, we've modified these scripts. And one of the things that I'm showing here is the linker scripting language. And what I've done here is I've made it, you can see, very easy to take advantage or to utilize the different memory blocks within the Aurix. So just by modifying this H file here, I can place memory in DSPR0, DSPR1, some of the different LMU RAMs, etc. And then we can evaluate the performance increase or decrease based on where things are located in the Aurix memory space. And then further, we can look at the tasking tool set and see how different optimization settings, et cetera, can increase the performance of your system. So where to begin? We want to start, if we're doing a comparison on performance improvements, we need to start from a base place. And so what I've done here is I've created a base default configuration where I've identified the frequency of operation, and then I've identified, or I've set the system resource interconnect, the system clock unit, timer module, the different frequencies of operation. So again, we have a common reference point. The data is initially going to be placed in the default application memory, otherwise known as DAM memory. And as Neil highlighted earlier, by enabling the program and data cache is what we ultimately want to do. So let's show what happens when we disable it. We will also disable data from being placed in the near memory or the first 16K of a 256K block. We will initially disable all benefits of the compiler. So we'll be running at optimization level 0 with a trade-off of 4, which will be emphasizing on size. And then we will show that in an upcoming slide. We have disabled the hardware FPU. So we will be basically all floating point calculations. We'll be using library calls. And then we're going to be running the tasking customized MBench application from CPU 0. So I've showed here a basic high-level snapshot of part of the Aurix architecture. So you can see here, I'm showing 5 of the 6 CPU cores. I'm showing the memory here, and I've also highlighted the local system resource interconnect area and the remote system resource interconnect domain. So as I mentioned, we're going to be running the MBench software out of CPU 0. We're initially going to run constants in code out of the PF0 block, and then we're going to be running data out of the default application memory 1 segment. So let's take a look at the LSL or the linker script language file, and then the map file, which are 2 pieces of the tasking toolset, which can greatly aid you in your development process. And so if we take a quick little snapshot at page, I don't know, 8,000 of the user manual, you can see here that the address range of program /0 starts at 8,000. And then if we look at our map file here, you can see that all of the different code here for the MBench, is actually located at that address. So just a quick little verification here that we're actually doing what we say we're doing. If we look at the data segment here, you can again see that the address range for the default application memory starts at 9041. And then again, if we go to our map file here, we can see that the map file actually shows default application memory 1. There's 2 different 32K blocks, so you can see that we're utilizing both blocks, and then you can also see here that the data is placed at the address that we say we're placing it at. So we're going to go ahead now and we're going to run the benchmark and what happens. And so our MBench data is we're going to transverse, throughout the architecture. We're going to go to the DAM1 memory block, and then we're going to return back to MBench. Looks pretty simple, straightforward, but as in all engineering problems, the devil's in the details. And so you'll notice right here that we've hopped over this little bridge right here to go from the local SRI bus to the remote SRI domain. And what you'll see here by referencing the user manual is that we basically added 13 wait states on a read and 7 wait states on a write. And this is again additional latency that's due to crossing over this bus. And so unless you know where to look, this could be this could be one of those problems where you're scratching your head. So let's go ahead and run the MBench, and what we show here is that we get an overall execution time of about 281 seconds, and so not very good, but as I've already detailed, we kind of set up the use case a little bit so that we can show some of the advantages of the Aurix architecture as well as the tasking toolset. So here's a quick little snapshot here of the debug perspective from within the Tricore toolset. You can see here that up here from the console log, you can see each of the cores. You can see different variables that we're tracking within memory. You can access the values of different registers. You have a disassembled view available, and then you can see here, this is the remote terminal or the terminal window that we're using, and you can see here the 281,000 281,000 milliseconds. Units are important from the previous slide. So let's go now and look at some of the performance aspects or details that we want to highlight. And so the first one, as Neil has addressed, is that let's go ahead and enable the Pcache. And we do this by basically clearing this bit. And if we look again at the user manual here, we can see by this bit here, if we clear this bit or write a 0 there, we are enabling, we're doing a cache enable. And then if we go ahead and we run our run the bench, the mbench example again, you can see that we basically improved our performance down to 206 seconds. Let's look at enabling just the Dcache by itself. So and then we'll look on the next slide. We'll look at enabling Dcache and Pcache together. So very simple again and straightforward to enable the data cache by clearing bit dcon 0. You can see here within the Aurix user manual again, this bit right here that's highlighted. And then by going ahead and running our performance, you can see that we've increased our performance by another percentage, which we'll summarize on the next slide. So let's enable both Dcache and Pcache at the same time. And you'll see here that now our improvements, you'll see the great improvement in our performance down to 105 seconds. And then if we look at a quick little snapshot, you'll see here by enabling program cache by itself, we see about a 26% improvement. Data cache, we see a 26% improvement. But by enabling both, you see a 62, almost 63% improvement. And again, that's by 2 bits. That's by enabling or disabling 2 bits. And so you can see, performance, can be a very fickle thing. So as I mentioned a couple slides ago, we're running our the default configuration off an optimization level 0 with a trade-off of 4. So let's look at a little more details into the optimization settings of the tasking toolset. And so we have defined some 4 different predefined configurations where we go from none to optimize, optimize more, and optimize most. The system will default. So if you create a project within tasking, it will automatically default you to optimize more. You can see from the trade-off setting here, which is also available within the GUI menu, is that you can either, you can focus your optimization towards speed with level 0, or for level 4, you can focus it on code size. You always have the ability to go in and do a custom optimization. So you can set or clear the different features of the optimizer that you want per your application. A lot of times, from an MCAL, an Infineon MCAL release note, or from a BSW provider, you will get some release notes, and those release notes will specify, hey, in order for this code to be MCAL 1.43 compliant, you must make sure that these compiler settings are set. And so here within the GUI, you can see an example of how to enable or disable some of the different optimized features. I've shown here some examples here of the different levels of optimization, and I've also showed some with trade-off of speed and some with trade-off of size, and you can see some of the overall benefits that that are gained with your program execution. So you can see here by going to an optimized level 3 with speed, we see a 32% improvement. You can see over here the code size as well, as so by going with a trade-off of size, you can see that we can see up to a 49 to a 50% improvement of code size. So again, this is dependent on your use case. Are you trying to squeeze the last little bit, say, out of a 3.6, second generation part before you move to a 3.7 or a 3.8? And if so, you may want to focus your optimization on code size. There are some bewares, however, and those bewares is that if you go to, say, for example, an optimize most or a model 3, There will be automatic inlining, which will automatically kind of that come along with the optimize most, and that can make it, you know, a little bit difficult to debug. Also, if you do like an optimize 3 with a trade-off 4, you will get COCO functions or code compaction functions. And this is where if you have 3 or 4 different adjacent assembler lines that are the same, the compiler will go ahead and implement that as a function call so that you can save, you know, code space. But at the same time, now you're doing function calls. And the last thing that I'll say is that when you do use things like 2 and 3, optimize level 2 and 3, is that debug symbols can be optimized out. Because again, at that point, we're trying to make the most efficient code as possible. And so we always recommend that you at least do a level 1 during code debug so that you know, don't, you know, aren't scratching your head wondering, hey, where did that debug symbol go? So let's take a little bit deeper look inside of the into the map file. It can be very, very useful. And so if we look here at the SIGNIU function of the of MBench, you can see that this particular benchmark, it simulates an extended Petri net, and it contains a large amount of if statements. So more than 250 statements. And then we can see over here how the compiler handles that. And you can see here again with an optimization level 0 trade-off 4 that our performance is for just running this single function, you know, we're at like 23 seconds. Now notice what happens here when we go to a trade-off 4. Optimize 3 with a trade-off 4, you can see we get an 81% improvement in code size, but look, we've actually decremented our performance by 54%. So this is again where the devil is in the details, and some of these functions, based on the routines that are running for optimization, you need to pay particular attention, you know, to what you're trying to do or gain by using the optimizer. So let's take a look here at how the code size is determined. And so I'm showing here the LSL file. And you can see here that we've created a SIGNIU code group. You can see here the mnemonic.txt. If you go to the tasking user manual, you can see that .text is representative of program code. If we now go to the map file and we highlight here the SIGNIU code area, you'll see that we have an address range here of D6F0 to 5E14, which is where that code is located. If we do a simple subtraction, you'll see we get a 78 DC base 16. If we do that conversion to decimal, you'll see 3940. And then again, if you look at the example here running in the tasking debugger, you can see the code size of 3940. So there's no magic. You know, the LSL files and the map files provide you all the data. It's more of knowing where to look and what it can do to help you. So again, if you have questions, you know, that's what Neil and I are here for. So you know, it's an 8,000 page user manual it can be very hard to find what you're looking for. So don't hesitate to take advantage of your resources. Neil talked a lot about cache coherency type topics. And so there is a register, the PMA0 register. And what this register does is it highlights cacheability for each one of the cores. And so for example, segments 1 and 3 through 7, 3, 4, 5, 6, 7, this here allows access to the CPUs, the individual CPUs, program and data scratchpad RAM. You'll see here that by default, so without doing anything, this PMA0 is going to provide cacheability for PF0 and LMU and the LMU. And so that includes the DLMU, the LMU, the default access memory 0, the default access memory 1, and the EMEM. And so if you want to be careful and not get caught up in this cache coherency topic, you may want to disable this LMU cache, and you can always disable this LMU cache by going to segment 13 or segment 11, I'm sorry, which basically means your LMU and your EMEM are now non-cached. And then you can see here from within the code example here, how we've used this language extension here to basically set PMA0 to either having LMU and PF0 cache set or not set. And then you can see the performance gain. So here with PF0 only, we're seeing a 45% improvement with both PF0 and LMU enabled for caching. You can see that we gain, maybe almost another 20% improvement, but with that 20% improvement comes the risk of cache coherency. And with that, Neil will talk a little bit more on the cache coherency topic. Neil, are you there?
Sorry, it was on mute. Right.
Technology.
Well,
yeah.
Yep. Amazing. So when we talk about data cache, it's important to remember that the data cache is always 256 bits or 32 bytes wide. So just in this example, let's say I've got this array of 8 32-bit values in DLMU0, and I'm accessing it from both CPU1 and CPU2, and their data cache is enabled. So if I read from CPU1 and CPU2, I'm going to read in that memory from DLMU0 into the local data cache now of CPU1 and CPU2. So if they're reading, let's say CPU1 is reading element 4, CPU2 is reading element 7, it's going to fetch that entire 32-bit or 32 byte in one go to the data cache. Now, if at a few milliseconds later, let's say that CPU1 makes an assignment to that third element and changes it to a 9. So now in CPU1's local data cache, it's changed to a 9. And because that hasn't aged out yet, that doesn't get written back into physical memory in DLMU0 yet. And perhaps at the same time, CPU2 updates a different entry in its data cache. So it's setting the second entry here to 8. So now I have 2 different copies of the same data in different CPU's data cache. Now, at time 30 milliseconds, perhaps CPU1 is going and accessing other parts of the system, and that cache line ages out. So now it does a write back into memory, and it's updated that third element of 9 is now written into DLMU0. But the problem is now if CPU2, if we look at its data cache, it's still got its own version of that. So now I have a cache coherency issue. CPU2 thinks that the data is different from what's actually in DLMU0. And now if I look a few milliseconds later where CPU2 ages out of its cache, now it writes this into DLMU0 and it steamrollered the change that CPU1 made because that cache line is 256 bits wide. So that's a reason to be very careful of cache coherency on the Aurix. And we could have used the non-cached addressing if I started this with segment B, that would bypass the data cache and take care of that problem. But there's a performance penalty for doing that, right? For bypassing the data cache. So you can either use uncached, or you can turn data cache off, or you can manually manage the cache by using the cache I instruction or cache a.i. And I've got an application note coming out in the very near future on this. Hopefully it'll be released within the next month or so. So that's what you have to be careful of with the Aurix architecture. And that's one of the most common mistakes that people make when we're talking about multi-core, sharing multi-core data. All right.
Thanks, Neil. So let's take a quick view here at each of the memory blocks within the Aurix and the performance that's associated with them. and you'll notice the disclaimer here up here that the data cache has been disabled. And the reason why is with it being enabled, the performance measurements were indicative of the cache and not the referenced memory block. We can see here that as kind of expected, this default application memory over in the remote SRI bus, you get those extra wait states by going over that little bridge. And so our performance, is a little bit worse there. And then you'll see as we move closer and closer and closer to the core 0, because remember MBench is running out of core 0, you'll see that we get, we'll get that we'll get the slight performance increase there as we move to memory closer to the core. Now, this is an interesting exercise here of using the user manual. And so what I'm doing here is I'm referencing table 71 in the Aurix TC3X user manual. I've called out, the version and actually the section where to find it, because as we've mentioned several times, if the manual is a bit arduous, and if you don't know where you're looking, sometimes you can't find it. And so what I'm highlighting here is that if you look here at a data read from DSPR0 from the local CPU. So remember, we're running it out of core 0. So if we were actually using DSPR0, then we would have a 0 impact, but we're focusing on DSPR1. So DSPR1 is located on the local SRI bus. And so you can see that we have a 7 wait state or a 5 wait state delay from doing a read or a write. You'll notice here from DLMU1, so a data read from DLMU, again on the SRI bus, you'll see also a 7 and a 5 wait state. And then here, if you look at our LMU data here for LMU0, so again, there is no LMU advantage necessarily for being a local CPU. So we move over to the local SRI column and you'll again see the 7, 5, and the 3. And then if we come back here and we look at our data, you'll see that the data is all basically the same within a tick here or there. And it's always nice when your empirical data and then the data from the user manual kind of aligns. So if we take a quick little view here, again, the 30,000 foot view of the Aurix memory map, you can see here, I've tried to color code here the data where, the brightest green here is the highest level performance. And then as we move away here, the performance goes a little bit lower. So you can see here, again, as we move away from core 0, that our performance slips a little bit. And then you'll see DAM 0 and DAM 1 memory here bringing up the rear. So one of the key features here is floating point within the Aurix. So all Aurix cores have a dedicated FPU or floating point unit for that optimal floating point performance. It's important to note that with the Aurix 2G or the TC3 family, that you're going to get single precision data with your FPU. But if as we move into the TC4, which is coming out, we'll get a bump up to double precision and some other positives coming from the next spin of hardware that's will be available probably within the next year. So if we look at floating point models, you'll see that tasking provides 4. And you also have the option to do a custom. So if we take a look here at some of the differences, so if you look at 0, which is IEEE 754, this is a strict double precision type library, and you'll notice that float point tramp handling is enabled. So this would be highly safe. However, it's going to be really, really slow. If you look at Model 1, the compiler can optimize for faster computation. Floating point trap handling is disabled, so it's still precise and a little faster. As we step up to Model 2, which is fast double precision, again, we're still precise and a little faster. And then the ideal case is that if you use floating point Model 3, you're taking advantage of the Aurix FPU hardware. You'll notice here that all checks are omitted, but you're still precise, but you're really fast. And if we look at a comparison here, you can see that I've grabbed 3 of the different functions here out of the MBench suite. And then I've ran them here with just using the software floating point library. And then you can see some of the performance differences here, where if I go to a floating point model 0 for double performance, you can see the drastic slowdown here in performance. But the ones that I really want to highlight this cubic benchmark. So you can see with floating point model 0 or the IEEE 754 that we're at 21 seconds. You can see if we use the actual hardware, we're down to 362 milliseconds. So we're still precise, but we're blazing fast. So if you don't need that double precision, if you don't need that float handling, by all means, take advantage of the hardware. And a lot of people will say, well, where's the difference come from? And you can see here again, if we refer to our map file, which I've talked many times, it's a very, very useful tool. You'll see here from the floating point model 3 call graph versus the IEEE 754 call graph, you'll see the addition of these 2 double precision function reads here that are required, and it's in doing these, accessing these function calls here that we lose all of this performance. So now the summary. First summary, let me say. So performance, it's a fickle thing. And so what I've done is I've split this up into Aurix features, and I've split this up into tasking Tricore features. And if we look at our starting point here, I've kind of cheated a little bit, and I've made our starting point worse than our default configuration. So you can see what I've done here is I've added this IEEE 754 double precision, and we're at like 320 seconds. From our default configuration, which most of our measurements were on, which you'll recognize our 281 second reading here. So using a custom FPU, which is actually a software library call, you'll see that we gain basically 12% improvement from going from the double precision to using just a standard library call. If we go over here and if we look at, like, if we change default application memory 1 to LMU 0, you'll see we have a 12.5% improvement. And then if we go from LMU 0 to DSPR 0, you'll see we have an additional 11% improvement. Now, the key thing here to recognize over on this side here of the flow diagram is that cache is still disabled. And so we're still not seeing the impacts of cache. So we're basically seeing the impact of taking the data and moving it closer to the core that MBench is running out of. But we still have, you can still see again that slight performance increase. So now if we move back over to our default config line here, and we go ahead and we enable Pcache, as we've already seen, we see a 26.5% improvement. Enabling Dcache, we'll see an additional 49% improvement, or which gets us down to our 105 second read or application time. And now if we go ahead and we move data from the default application memory space to the local core, you'll see a very small negligible improvement of an additional 0.5%. And again, the reason why is because cache is enabled. So we're already seeing a majority of the benefit. We're already seeing a huge amount of the benefit, but by moving it inside to the local scratchpad RAM of a core, we gain some additional performance. You'll notice the color coding here that's going on. So purple would be Aurix special function registers. So these would be where we have to set bits or clear bits. The pink color here are for the linker script language additions, where we locate or we specify what part of the memory space that we want to put a particular code segment in. So now let's move over and add in the Tricore toolset. So the tool set hasn't been involved yet. This is all basically, Aurix performance information. So now let's go ahead and let's change our optimization level to optimization level 2 with a trade-off of speed. And you can see another huge performance step or an increase of like 43.9% improvement. If we go ahead and just go to optimize most and go to the optimization level 3, you'll see an additional 8% improvement. If we now change from our software library call to actually taking advantage of the FPU hardware that's available on each core, we see another huge performance jump of additional 22.7%. And then there's a topic which I haven't covered. I didn't cover here within our discussion. It's mill linking. Mill linking is an advanced topic, and we can take that offline if you'd like. You'll have my email address, at the end of the discussion. But if you refer to section 11.2 of the user manual, what mill linking is it basically applies all those optimizations application wide. And this can yield significant improvement, but it will significantly increase your build time. And if you think about it from a 30,000 foot view, you're basically taking everything and you're throwing it into one big pot. And then you're going to take all of your optimizations and you're going to apply them globally. High safety levels like ASIL C and D, they don't recommend or they don't like mill linking since everything is all mixed up. But it just shows you that by taking advantage of this, you can gain an additional 6.9% in improvement. So let's do like a quick little, what have we done here? So we've basically set 2 bits. We've added 1 LSL entry, and we've adjusted 3 tasking toolset options, which are all highlighted over here. And we've basically seen almost an 88% improvement. So again, you can see how fickle performance is by accidentally, not clearing a bit or something. You can lead to a significant degradation in your performance. One of the things that we'll talk about in the conclusion is that when you create a new project within tasking will give you some C start files, and what those C start files are is they basically set these special function registers. They, do some trap vector work. They basically do a lot of the bookkeeping to get your Aurix up and running. And it's very important that as an application developer that you don't assume that those C start files are correct or that they're dialed in for your application. And so it's very important that you look at those C start files and make sure things like your cache is enabled, for program and data, and that your settings, are correct. Don't assume is the end message. So the last topic that we'll cover is the performance core versus efficiency core. And so this is kind of more of an older topic, but it's interesting. So I wanted to put it in here. So if you look at we did look at the TC27. And so the TC27 does have a performance core as well as an efficiency core. And you can see here the differences is that what a performance core is it's going to be optimized for performance. So you're going to get about 20 to 30% increase in performance if you use a performance core. It's basically a superscalar Harvard, so it does multiple instructions per cycle. It has 6 pipeline stages. It does dynamic branch prediction. The key point here is that it is identical instruction set to the efficiency core. And then if we look at the efficiency core, oddly enough, it's more for efficiency. So you'll see a 30% reduction in power compared to the performance core. And the kind of the things that come along with that are that it's only a scalar Harvard architecture. So it's only a single instruction per cycle. There's 4 pipeline stages operating at 200 megahertz. And then if we look at the performance difference, you'll see that with the performance core that you get about 11% improvement. So again, if you're working on an Aurix 1st generation family, so that would be either the TC23, the TC26, or the TC27, which have efficiency cores. It's a matter of, again, like the common engineering problem. Do you have a power dissipation problem, or do you have a performance problem? Do I use my performance core more? Or do I use my efficiency core more? And with that, we're going to move on to some advanced topics. And for the advanced topics, Neil's gonna take us through some of these.
Right. So we've talked a lot about moving data to be nearer the core that needs it. But even if we say move all of the variables to DSPR 0, there are still some more tricks we can do to improve performance further. So by default, data is allocated within just the full 32-bit address space of the Aurix. But there are a couple of architectural shortcuts that we've got. So if you're talking about the first 16K of each segment, and each segment is just that first nibble, so each DSPR is in a different segment, and then overall DLMU is in its own segment. The first 16K of that, we have a special near addressing mode that can use less instructions. And the same thing with, we have 4 address registers by convention, A0, A1, and A8, and A9, that can be used as a plus or minus 32K offset. So you can have data based on the base address of that and then have an offset based on it. And these are things that you can set up in your linker to place variables and get that performance benefit. So if we look at, let's say 2 assignments, then the assembly code that those end up looking like for these 2 assignments is 5 instructions. I've got to come up with the 32-bit base address, the upper 16 bits, and then add on the 16-bit offset to that. But if I use near or small addressing, then I'm using just that 16-bit offset. So that instead of being 5 instructions for these 2 assignments, is just 3 instructions. So obviously, if I have less instructions, I have less P-flash space, and it also executes faster. So that can be a really big benefit, especially in the single core systems. You have the option of combining all 4 of these base address registers. You can use all 4 of them together to cover all of the local DSPR 0. And I've seen one customer where we did that optimization, just a few changes to the memmap file in that case and the linker file, and we ended up getting we went from 95% utilization to about 70% utilization just in the space of an hour or so. So that can be a huge thing that is often overlooked. Another thing that's overlooked is to use the program scratchpad RAM on each core. So we've got this limited amount of RAM, but it's 0 wait state, so it can execute a lot faster than getting memory, fetching instructions out of program flash. So that's a matter of copying your code from P-flash into PSPR at startup, and we've got some linker examples you can steal from Infineon software libraries. So if your project's using the MCal or Safety Lib or our old Sheet Plus on the TC2X, you can just take a look at those LSL files in the case of tasking and copy those over. But the best things to put into program scratchpad RAM, and this can vary by your application, of course, but generally my recommendations are to put the trap vector table into PSPR. That can make a big difference, especially if you have an operating system that's relying on the syscall instruction to do elevated OS kind of stuff. The number 2 is to move the base interrupt vector table. If you have a system that is doing very frequent interrupts, maybe you're doing, say, 20 kilohertz motor control or something like that, jumping to that interrupt vector table is going to be much faster if it's already in program scratchpad RAM. And the third thing, if you have these high frequency interrupts and you can actually move those interrupt functions into PSPR, that can be a big help also. And lastly, if you can move operating system components that get called very frequently. So for example, if you take your task switch code and put that into PSPR, that can be a huge benefit. But it's not, in addition to using the CPUs, we've got very smart peripherals on the Aurix. So if you're not using these tricks, consider maybe adding those to your application. So especially in the case of the higher variants like the TC 36, 37, 39, we've got the GTM has sequencers in it. So you can actually run code within the GTM. So if you have very complex tasks that are maybe driven by a very deterministic little state machine, you can consider putting those into these GTM sequencers. It's very possible in the Aurix to use our direct memory access, our DMA controller, to move data around without CPU intervention. So where historically you might have tied, say, a QSPI transfer to an interrupt, on the Aurix you can have the DMA controller do that QSPI move for you. That really can help offload the CPU. And it's not just a matter of tying a peripheral to the DMA, you can also string these transaction sets together and come up with some really slick DMA transactions where it's handling much more than just a single transaction in one go. If you're not using the hardware security module for crypto encryption and decryption, you might consider using it for your application. I mean, it's there on the whole TC3X family. So that's another way to get performance. The hardware security module is a bus master in the system, so it can do anything that the tri-cores can do, modifying IO ports, communicating over the system peripheral bus, anything. There's also a standby controller on the whole TC3X family, and that's a small 8051 core. If you're not using it for anything at runtime, you could consider using it to, say, emulate a LIN interface or something small like that. Right, tasks that have a very high interrupt rate, if you really need that deterministic performance, you might consider moving those into that GTM sequencer or into the hardware security module if you're not using it for crypto operations or the standby controller. And using all these things together, you can emulate a peripheral that's not in the hardware. So the standby controller, for example, might emulate I2C, or you could do the same thing in the hardware security module or in the GTM.
Great. So let's look at some key points to remember. The first point is, of course, always ensure that your program and data cache are enabled in the CStart files for optimal Aurix performance. Remember to check those files and make sure that they match your requirements. Don't assume, again, that they're correct. The tasking optimization settings can be used to trade off between minimizing code size and maximizing code performance. And don't forget to use -01 during code development to prevent your debug symbols from being optimized away. Keep those constants and data in the near small memory. And you don't have an unlimited amount of that memory, so make sure that you prioritize, the frequently accessed data, in that near memory. Performance gains from caching LMU can lead to cache coherency issues if you're not careful, so please refer to the Infineon application note coming soon for more details. The tasking linker will automatically place code to get your application up and running quickly. So for safe and optimal performance, to minimize stalls, for example, take advantage of the tasking LSL and map files. And finally, floating point calculations can be extremely burdensome on your resources. Be sure to take advantage of the FPU hardware where you can for optimal speed and precision.
All right, so knowing the Aurix architecture is really critical to achieve the best performance on our system. And we've got a lot of features and tools to help you measure that performance internally and externally with debuggers. And we can definitely help with training and multi-core tools. And there are thousands of pages to read if you've seen our user manual, that's for sure. But we're here to help. So we've got our email addresses at the bottom here. If you need to learn more, you can visit the Infineon forums. We've got an area just for the Aurix, and Tasking has their own forums also. Oops.
Great. Thank you very much, Neil and Roger, for your presentation. We have already a few questions popping up, and I think we still have some time to do the Q&A session before we start this. So as you see on the slide here, if you have any questions you always can directly drop us an email. Also in regards of any request on evaluation licenses, and also if there are any questions on the Aurix hardware, the microcontroller, we can then forward this one to Infineon, to Neil, and I'm sure they will be happy to get in contact with you. So now let's start to answer some questions. So we have a question here. I will read it. You mentioned map objects in RAM to balance the performance. Can you elaborate a bit more on this? For example, which is recommended to goes to DLMU, LMU, which goes to the DSPR, and the reason why?
Neil,
Well,
do you want
that's
to
a
take that one?
yeah, that's a great question, and it really
Yeah.
it really depends on your application, right? So I would be I would definitely, if you have things like high-speed algorithms running, keeping that data that algorithm uses closest to the core that needs it is really important. So generally that's the rule, right? So to get the best performance, you keep that data nearest the core that needs it. And keeping, when you have global areas, like let's say you have global data structures that are being updated by multiple cores, then I would be careful to either keep that in a CPU's DSPR, and those areas are not cached by default, so you don't have to worry so much about cache coherency there, or to keep it in uncached LMU space. Mm-hmm. And that's the best way to avoid the cache coherency issues.
Thank you, Neil. There's one question because some of the audience missed the first 30 minutes and asked if this webinar will be recorded. Yes, this webinar will be recorded, and we will provide you an email by, I think on Monday, we will send out an email with follow-up, and you will then also receive the link to the recorded webinar. So you can make sure you can watch it again, don't miss anything. Let's move forward to the next question. Why is the data cache disabled by default?
So I don't think it is. I think at least with respect to the tasking tool set, you just want to make sure that you verify that it is enabled. And so those C-start files, a lot of folks, when they create a new project and the C-start files are moved into their workspace, the biggest thing is that, just don't assume that they're right. Make sure that you go through the register settings that are in there and just make sure that they, that how you need your application to run is indicative as to how those special function registers are initiated.
Mm-hmm. Right. And I don't have a great answer as to why the startup software, our internal boot ROM, leaves that disabled by default. But for sure, if you look at the Infineon ILLD or the Aurix Development Studio or our MCAL, for sure the data cache gets and program cache get enabled.
Thank you. So there are a few more questions regarding the data cache. I think this is some topic which is quite important to the user. So another question in regards to this topic, you mentioned the cache coherence is not automatically. What does this mean to the user? What additional work needs to pay attention in order to leverage fully benefits of cache?
Right, and that's a great question. That's the reason for coming out with this new application note, hopefully in the very near future. But the additional work that you need to do is either to, well, if you do want to use data cache and you have cache, you have a structure, let's say, placed at a cacheable address from multiple cores, then the important thing is that you need to make sure that the data that gets updated is either in separate cache lines, separate 32-byte areas. So you want to avoid having adjacent bytes or words get updated by multiple cores. Or you can manage the cache lines yourself. So we have within tasking the cache AI instructions to manually purge an entry from the data cache. So you can either force it to write back, or force it to be invalidated so that you read a fresh copy of data.
Thank you very much, Neil. Another question regarding data cache. Can we use program data cache while using overlay memory function?
Can you use it while using it? The overlay is dependent for each CPU. But if you were using the LMU area, I think you would generally access that uncached. I haven't seen an application where somebody uses the data cache, because that would be kind of precluding the whole purpose for doing overlay in the first place, right?
Thanks. Then a question in regards to lockstep. Is lockstep always core 0 running the core and core 1 lockstep to core 0?
Good question. With our competitors' architectures, you have the option of splitting cores or having them run in lockstep. But on the Aurix architecture, the lockstep always consists of a master and a checker core. There's no way to have them split and run separate core. And the question about, is it always core 0? Depending on what variant you're talking about, it's always the first cores that have lockstep. So for example, the TC39X, where we have 6 cores, cores 0 through 3 are lockstep, core 4 and 5 are not.
Thanks. Another question in regards to the handling of the core. By default, I use only core 0, but looking at the map file, I see data being stored in core 1 and core 2's RAM and then core 0. How do I get the linker to prioritize core 0's RAM?
So the easiest way to do that is through the linker script language, sorry. So the LSL file, you can go in and you can create groups for your code, and then you can specify whether you place them basically in core 0, core 1, core 2, in terms of the local memory. And then one of the, just to touch briefly again on the embedded profiler performance tool, one of the things that tool will show you is it will show you if you're doing like cross core memory accesses. So if you have something, say, running out of core 0 and it's accessing data that you've placed either on purpose or has accidentally, say, or an oversight has placed it into core 1, and it's leading to some stalls or some performance degradations, then that's one way of highlighting those types of cross-core memory accesses.
Thank you.
You want to add anything, Neil?
Nope, I think that's good.
In regards to this, another question, do you have a map file analyzer, for example, to sort for size of functions?
So there are, so the tool set has 2 different versions of the map file. So it can either do an ASCII version of the map file, which I showed you, or there's an XML version of the map file. Personally, my preference is to use the ASCII. You don't gain you don't have some of the advantages that an XML map file brings, but you also now have the search capability. So you can search for ASCII text, you can search for group names, you can search for symbols, and so my preference is to use the ASCII version, but you have the ability to generate one or both, when you're building code.
Thank you. So we still have a lot of questions. We are running out of time. Let's pick some more questions, and then maybe we can get back to the audience or the user who asked these questions via email. This would be my proposal. What do you think, Roger and Neil?
That's fine. If we have the email addresses, then absolutely we can do that.
Because I think we have still 17 open questions, and maybe let's pick 1 or 2 more.
That means either we did a bad job in explaining, or that there's a lot of cool things that people now realize that they didn't know about the Aurix and the tool set. Yes.
So let's take two more questions. Is the cache or the cache coherency problems, are they also possible with the 32-byte data buffers?
Definitely possible if your data is not aligned to a 32-bit address or a 32 bytes. So if it spills over, let's say it's aligned to 8 bytes instead of 32, now you're potentially talking about 2 cache lines instead of 1. But even if it is 32-byte aligned, yes, it's still possible. If the example I gave, right, shows how CPU 1 and 2 can still have fighting. But if you're separated by 32 bytes and they're both 32-bit byte aligned, then no, there wouldn't be a problem.
Thanks. And then there is another question. In the absence of a system requirement, is there a rule of thumb to judge whether to use single or double precision before software development begins in earliest, or does that only become apparent after system testing, controller and plant in brackets begins?
I think it depends.
Right,
it depends
right.
on your application. So if you're doing an ASIL C or ASIL D application, a lot of times within, if you reference the ISO specs, they're going to require that you have the trap handlers enabled, and they're going to require some of the aspects of IEEE 754, which is going to point you down the floating point model 0 road. If you're doing, I think if you actually do, and I didn't do that analysis here in this particular example that I've shown, but if you look at the actual precision difference, between the FPU and a double precision, in some cases, you're not gaining necessarily that much with your double precision data. So again, it depends on what are you trying to do? Are you trying to do, precise engine control or motor control, which requires double precision? Or, just assuming that, hey, the more bits that I have, the better my application isn't necessarily, the right way to go. I don't know, Neil, what do you think?
Yeah, I think it really depends on your application. So you've got to think about how many digits of precision you need to get your algorithms done.
All right, thank you. Okay, I would recommend that we now will close the session as we have still 16 questions open. Maybe there is one question we can answer from someone who does not show his email and his name. So or maybe we can answer this one. When utilizing the embedded profiler to characterize software runtimes and accesses, is there a visible overhead for the CPU, peripherals, buses in capturing this data?
So there's, I think I understand the question. So there's 2 different performance tools available through tasking, which are kind of work hand in hand. And so there's the embedded profiler, which is focused primarily on profiling or looking at, where the majority of your execution time is, what functions are taking the majority of that time, and then having the capability of diving down into the assembler and seeing what's happening. And then you also have the multi-core performance tool, which does things like look at load distribution across multiple cores. It looks at things like RTOS tasks, which tasks, from your real-time operating system are taking the most time when they're called, which tasks, say for instance, are putting a core into a overload situation, which are, you can set those thresholds through some menu systems. And so I hope that addresses your question, but I guess the thing that I would highlight is that, our partners out there like iSystem, for example, if you're using one of their debuggers, they have full profiling capability, the tasking tool set has capabilities. And so it's just a matter of using some of these tools that that you have at your disposal.
Okay, thank you, Roger, very much, and also Neil for answering those questions and also for your excellent presentation. So if anybody still has some questions, please drop us an email at marketing@tasking.com, and we will make sure we will get back to you. As mentioned earlier, this webinar will be recorded, and we will send you a follow-up email with a link to the on-demand webinar. And we will also try to answer all open questions and get back to you with the answers. Then thanks very much for joining, taking your time and showing interest in Infineon and Tasking's product. You can always check out our website for upcoming webinars and other events Infineon and Tasking are taking part. We wish you a nice and joyful rest of the day, and hopefully see you soon during one of our upcoming webinars. Thank you very much for joining.
Thank you, everyone.
Today.
Thank you. Bye.